So this week I'm talking about an implementation of the Voxelspace algorithm that I did in a compute shader. And so just before we start, I want to go over some some terms. So something that I thought was interesting, and I've seen this in a couple of older references to voxels. They call this approach voxel-based, even though it's not three-dimensional little cubes. We're looking at a two-dimensional array of columns of varying height. So that's kind of an interesting element. They are still volume elements. They're just not little cubes. So compute shaders, when you're working with those, you talk about the dispatch. So that's how big the job is in terms of how you invoke your shaders. So that's like vector processing kind of idea where you have some job that has an X, Y, and a Z dimension. And for each index in that, there's a job that runs. And we call those jobs invocations. So this is kind of from a time where there was some different approaches to real-time graphics. Things like sprites and voxels were kind of also in the running for mainstream approaches for graphics and things like that. But a lot of these voxel approaches were very heavy on memory. So we saw things like this, or where it's height map based approach, or very small volumes like Command and Conquer did some models that were voxel based. So if you haven't seen John Lynn's work, that's a very cool, more recent implementation that he's working on using voxels as a rendering technology. I think like more of a ray tracing kind of idea. So where this came from is this company called Nova Logic. But as best as I can tell, the guy who came up with it is named Kyle Freeman. And this was, at the time, it was a very impressive rendering technology, especially for real time. Kind of modern standards kind of color your opinion of it maybe, but it's the comparison to what was available at the time was it was very impressive. If you look at a game that was produced in a similar time period using polygons for terrain, this really was a much higher fidelity type of operation. So just real briefly, what the data looks like. When you do this type of rendering, you've got a height map and a color map, and the height map tells the elevation at each location on the map, while the color map contains like a height gradient and demarcates where the water is and has baked shadows. So the way that the renderer works, the kind of naive approach would be to do this backwards approach, where you start at the back and you sweep across each layer towards the camera. So you have all this overdraw, and you just keep drawing over and over and over towards the viewer, which isn't very efficient. So they came up with this very cool method where they start from the viewer and go forwards. And so basically what that is it maintains a Y buffer, which is the height of so there's some logic to translate the sample of height into the height on the screen. And the Y buffer contains the highest Y value that you've seen so far in the rendering process for a given column on the screen. So starting at the bottom of the screen with the Y value equal to 0, you go down and you take your first, starting from the camera location or whatever you're going forward, and you get these height samples, and that updates continually. And so you're not drawing these spaces where this lower section is. You're not, you know that you don't have to overdraw in these sections. But when you get to here, when that height value becomes greater than the Y buffer, you begin to draw over again. So in the CPU-based approach, this is done like this in horizontal sweeps across. So basically, there's two kind of rays that go out to create kind of a wedge shape. And as you sweep across, you're interpolating between points on that wedge shape on either side of it. So that's that keeps the distance. It's constant across the along the view direction. That distance is constant. So basically, there are a couple of limitations to this type of rendering. If you notice, there's no way to do overhangs or caves. There's only a single height value and a color value stored for each location on the map. So it is kind of limited, but within the scope of what it's able to do, it's pretty cool. So this is where the compute shading comes in. Rather than doing these horizontal sweeps across, the Y buffer makes this a trivially parallelizable problem. So if you think about it, each column of pixels can be its own job, where it basically goes and traces a ray out across the terrain. That ray surfing kind of idea where it's maintaining the Y buffer. This can happen independently for every strip of pixels horizontally across the screen. So this is what I tried to do is just going through and having each of these, like doing a one-dimensional dispatch that was just by columns. So the way that I generate the rays is a little bit different, and the reason for that, there's a couple of, well, I was just kind of playing around with it a little bit, but the way that I did it is I map the range from 0 to the width to the range -1 to 1, and I use this to rotate vector to two-dimensional vector that indicates where that ray is going to be going across the terrain. So a couple of different little things. Sometimes this gets a little messed up, or you can intentionally mess with it. Widen the FOV so you are seeing multiple loops around, kind of thing. So some silly artifacts, I guess. But then this side-to-side offset gives you the ability to do like an orthogonal type of thing. So now instead of starting from a common ray origin, you're actually each column now has a starting point that's offset, and that's just taking the cross product of that direction vector with the a vector pointing up, and then that gives you that side-to-side vector. So that side-to-side offset actually introduces this kind of curvature. So that's where that comes from. So this Marat Esau, I think, this is the implementation that I saw, and it's what got me excited about it. I really like this guy's minimap. A couple things about it. It's done on the CPU, and it's done back to front as an isometric scheme. So it's a little bit not the direction that I was trying to go, but I ended up replicating something similar using the forward approach, but masking out a circle about the viewer, rather a circle about a point in front of the viewer, so that you have some view in front of the view position. So if you see here, it's kind of circular about some point in front of the viewer a little bit. And that's done as a second rendering pass into an RGBA render texture. There's a first pass that does the main view, and then there's a second pass that comes in and does the it's a smaller dispatch. It's only in this corner, but yeah. So for each vertical strip, it's doing the exact same thing, just with some hard-coded parameters. So some little things that I did with this, messing with the edges. If you just color them black, you kind of get this border. But something cool that I was messing around with, if you set them to clear or to not draw, when you do this this minimap pass, you actually get this kind of appearance of a floating surface because of the way that Y buffering works. When you draw that clear strip, it actually precludes any further drawing on that column. So you get this this effect. One other thing I tried, and this is the same type of rendering. It's done by a game a couple of years later called Outcast. And basically what they did to extend this algorithm was to filter the textures. And I'm not really sure if I care for this so much, but it is definitely smoother. So where you see the nearest sampling artifacts in this, this actually goes through and does linear interpolation, bilinear interpolation, and gives you a sort of a smoother surface by interpolating between neighbors. And I found that you do actually have to take denser steps where you start to get strange artifacts on some of these slopes. And I mentioned earlier that RGBA render target. I kind of came up with a way to use that for depth fog by using the clear color as the fog color and having a fall off with depth, basically. So as depth became greater, the alpha channel becomes lower, and you have more of the clear color show through. There's a few things that I'm not sure how many of these I'm going to be looking at doing, but maybe give some people some ideas. I was trying to do some bitmaps, but it's not going to be able to automatically do that the way that bitmaps are generally used by looking at the local difference in sample position. So I would have to manually interpolate between the levels of detail as you get farther away from the viewer. But a few things like, okay, so to deal with that curvature, you could project the direction vector onto the forward vector and kind of normalize the length with respect to that vector. Then, yeah, so with the minimap, we have this hard transition to a black color. You could instead kind of have that that fall off and be sort of more clear, or more towards some color than being a hard transition there. And I'll get into this next point in a second. But then something else that I thought about, because especially Outcast did polygonal rendering over top of this. And if you notice back a few before that, there's actually sprites rendered over top of the world in this game in Comanche. And so a way you could do that is by keeping a depth buffer, which effectively I'm kind of already doing with the alpha channel. But if you kept the X and Y of the world in like red and green kind of idea, you might be able to do something where you click and then read from that buffer to get the world X and Y. And that might be some interesting way to interact with the map. So the reason that I started doing this was to visualize some 2D hydraulic erosion sim that I had messed with a little bit. What I had before was just generating a grayscale height map, and you started to see where the rivulets form as more and more particles erode the surface. So something cool that I figured out a way to do this multi-threaded without stepping on any toes with the OpenGL API. There's a worker thread and then there's a main thread. The main thread is responsible for all interaction with the OpenGL API. But this worker thread is working in the background to do the simulation update and prepare the textures to send. So basically, there's a certain job size that you give it, and it'll run that many particles. Then it'll prepare uint8 buffers for the height map, and it will compute normals, which is part of the hydraulic erosion sim for accelerating the particles downhill. And then when it finishes this, it sets a flag, which is checked by the main thread. So the main thread sees that this is complete, and well, okay, so it checks to see if it's done. If it's not done, you're just going to do a regular render pass with the existing data. If it's done, then you have new data to send, and it's just a GL buffer. No, it is a GL text image 2D to send that uint8 buffer straight to the GPU. So what those computed normals look like is kind of a little bit obnoxious, but basically this gives you a way to do some basic lighting. If you take a dot product with that computed normal and vector pointing straight up, you can see that you get kind of highlights on flatter sections, and slopes become darker as they become steeper. And if you apply a color gradient to that, you can get some kind of neat effects. And also this does tiling of the image textures. So as you get farther out and into the distance here, you're going to start seeing some repeats of the geometry because it's just repeated. And that's to deal with having a texture that's 1024 by 1024. So if anybody has any questions or whatever, this is where I got some information. Sebastian Mack has a really great explanation of the specifics with source code if you ever want to pursue this. And some of the animations that I have are from that page. It's the first thing that comes up if you look up Voxelspace. The 2D hydraulic erosion sim is by Nicholas McDonald. is the one that I referred to. And that's that link here. And then this was shared by someone in this group a couple weeks ago, and that was very helpful to kind of explain what was going on with Outcast, the bilinear interpolation, and the ray surfing. Because that's a hard thing to find information about now, because it's kind of a legacy technique, I guess. There's been a lot of search engine optimization with respect to voxels, and you really can't find anything about it anymore. So yeah, sorry, I don't have the chat up, so I can show off what this looks like running.
I was about to ask if we could see it running the. Is this the erosion one?
Yeah, so I can show off both the erosion and the thing I have it set up, so it'll do both. Just one sec. Yeah, okay. Everybody see that?
Yeah.
Cool. Okay, so this is the hydraulic erosion sim running. So I can adjust the job size here, and you really only see it when you're up close. The second to second kind of updates here. You see, you'll see little changes in the surface height and also color from the normals. But as you turn up the number of steps that are taken per update, you see that it takes a little bit longer to generate an update, but you'll see more significant effects. But at the same time, the renderer remains responsive because that's all happening in a separate thread, and it only has to sync when that job finishes. So actually pretty pleased with how that turned out. But yeah, the you do see with textures this size, you do see some repeats. The couple interesting things, the way that they do up and down tilt is by adjusting where the horizon line is at, and that has to do with how the height on the screen is computed, and that that project that I referred to, Sebastian Mack thing, has a much better explanation of how that works. Because it has an offset that recedes as it gets farther away from the camera. But yeah, so you can kind of see where these flows start to form, and over time you see kind of glacial movements of material down from higher points to lower points. But so for different maps and things, there's a whole bunch that are provided by that repository, the Sebastian Mack one. And so this is the one that I had pictures of in the talk. And it looks a little funny because I have mirrored repeats on rather than just regular repeating textures. So you get some features that are close to one another. But then, so there's a number of different maps that he provides. I think there's almost 30 of them, the different variants and stuff. But so, I guess, yeah, so you see these sort of almost Minecraft type cube shapes when you get up close to things, and that's from the way that these columns are read, and that comes from the nearest sampling. So if you go in here and turn on linear sampling and load a map, and unfortunately it only toggles it when you load a new map. But anyway, the yeah, so you see where these lines kind of curve, and you see these slopes where you're interpolating between neighboring sort of volume elements there. So yeah, I'm not sure how big a fan I am of the interpolated values. Honestly, I think that there's a lot of charm to that that nearest sampling look when you get up close and you see all the cubes, or sort of cuboids, because they're really just tall rectangular prisms, columns, sort of. So yeah, does anybody have any questions?
I guess
sorry.
I'm still not exactly sure how that web buffer works. So when you mentioned that you say you set the draw into clear, then it will just not draw anything. How does that work?
Sorry, I'm not sure if I quite followed exactly what you're saying there. So you like, okay, when you for each column here, you're starting at the very bottom here, and it's initialized to 0. So you start at the view position and you're going forward. Now, for the first few steps, it's actually down below the camera, and what you're seeing is that those values are negative. So they won't be drawing. But as soon as you get far enough away from the camera that a height value translates to a positive value, it's going to start updating. And you see where each of these columns kind of becomes taller and taller on the screen, going off into the distance.
Oh, I see.
Does that kind of make a little bit of sense?
Yeah.
But and so using that distance from the camera is kind of how the depth fog is implemented. There's also a term that changes it by height, the height of the viewer, so that it's got a little bit more natural scaling.
So yeah, I also wasn't sure about like when you for the mini map part, you said that to draw the clear value and then it keeps it transparent. That part I didn't really understand.
Okay, sure, yeah. So this actually takes a second. I'd have to recompile it with another. I should have had a toggle for that, but basically, so you saw before where it had that kind of round section below, and those edges were kind of you saw it like. Let me bring this back up. So on these side pieces, because I'm masking out a circle, or like a circle around that viewpoint, I'm getting 0 reads outside of that, and then when I hit the part that's masked out, or that's not masked, where I start getting non-zero reads for color and height, you see these kind of vertical strips.
Yeah.
So basically what I'm doing instead of that is I actually have a slightly smaller mask. And this illustrates that a little bit. With a slightly smaller mask, it's like radius of 100 versus radius of 95 or something like that. And if it's in between those two values, writing black here or transparent. So it's basically just not drawing.
Okay.
And so that's how I got that effect around the edges. So instead of drawing those kind of sort of extruded, the whole column on the edge, it's actually just not drawing it, or drawing it in black, or just not drawing it kind of idea.
Okay, that makes sense. That's cool.
Yeah, I have a question. That's really cool. Did you try to use much bigger maps than 1024?
No, I didn't. This was as big as I tried, because this was the data that I had. Let me this repository here. This is the one that I referred to, and this is where I got some of the animations from. They share some images that are the maps color and height, and they were just some standard size. I haven't experimented too awful much with producing my own beyond just the erosion stuff, and I haven't done any shadow stuff either. That's something I want to mess with on that erosion thing as I'm doing the height gradient and the dot product for the lighting. Also go across the texture and kind of check for occlusion.
In the 90s, I actually tried to implement that. And
nice.
Yeah, and I used, there were tools around where you can generate these maps. And then later on, I think 10 years ago, we actually built a helicopter simulator, and we used similar tools. I think they are called World Builder now. The original ones were really low res, but there are newer tools where you can actually really generate one color and one height map, and then take those as an input.
That's cool. Yeah.
There's also this book here. I don't know if you ever saw this.
I don't think I have.
1994. Peter Friese, or Friese, depending on how you pronounce it, described a similar algorithm in there. He actually works now at Unity, but when I saw your algorithm, this was really close already to what you used at the time. This is fun because the idea of having this whole little engine running in a computer, it's fun for engineers, and maybe we can also do something with that on mobile phones.
I hadn't seen it done before. I thought it was a neat idea.
Yes.
And just looking at the structure of it, I thought that was a really good fit. So there's a two-dimensional dispatch that generates the color map from the that height and normal data. So that would be where I do those occlusion checks if I do implement that. Cool. Does anybody have any other questions?
For the minimap, you said that it was a second pass for rendering. So just curious, is it just to do the same rendering as the main rendering and just scale down?
Yeah, so I basically just messed around and found parameters for height and the horizon position and these types of things, and that pass actually only so it's a separate compute shader, but it only takes 2 inputs that are the position and the direction. So the rest is hard coded in the shader. It's just kind of simplifies that problem a little bit.
Cool. And then also in the repository, is there tools for generating the terrain?
This one, the Sebastian Mac one, it just has about 30 maps that are matching color and height. So the only generation that I did was it's a diamond square algorithm to generate the initial height map, and then there's the hydraulic erosion that happens onto that to produce the subsequent updates.
Okay, so you added your own generation tool, but the repo itself has just fixed maps, 30 of them, you said?
Yeah. Let me link that in the chat here. You can take a look.
Okay, thanks.
Yeah, that's a really good explanation if you want to try and figure this out yourself. It's he does it in like 20, 30 lines of Python.
Yeah, I actually played that game back in '92. It was the first experience for 3D that I had, even before Wolfenstein. So I remember this game.
Cool.
The Commander game, yeah.
Yeah, I've always thought it was neat. I guess I've known about this algorithm for a little while. It was just a few weeks ago I got it in my head to do this. Well, I kind of had the idea for a while, but I don't know. Yeah, I'm not sure exactly what the impetus was, but I decided to get started on it a few weeks ago.
Do you know if there's more modern algorithms for rendering terrain with height maps without displacing a mesh or something like that? I don't really know what the state of that is.
There are some ray marching stuff that does height maps. I know Inigo Quiles has done some with that.
So I was thinking, this seems like a pretty good technique, even like in modern day, just if you want to render it straight from a height map.
It's pretty quick too. Because it's like 1 to 2 milliseconds to do the drawing out to a reasonable distance. If you go much farther, well, it depends on where you set that maximum distance, because it's still doing texture reads out to that maximum distance, even if it's not drawing to the screen. So you have to kind of constrain that sometimes.